This is Physics 104A, Homework Solutions for Porterville College, Chapter 2. We start with number 14. Starting from home, it says you bicycle 24 kilometers north in 2.5 hours. So here I've drawn, here's home, here's 24 kilometers distance, and you drive bicycle 2.5 hours, and then it takes 1.5 hours to return home. And question A asks, what is the displacement at the end of the first 2.5 hours? So displacement is final position minus initial position. If we had this on a x coordinate system, x-axis, we could say the home is 0 and this is 24 kilometers, and 24 minus 0 is 24. Or just looking at the picture, you can see we are 24 kilometers removed from where we started. So the displacement, delta x, is 24 kilometers. B asks, what is the average velocity over that first leg? Average velocity is displacement over time. In part A, we got the displacement of 24 kilometers. Now we're dividing by 2.5 hours, and that gives us an average velocity of 9.6 kilometers per hour. Question C asks, what is the average velocity for the homeward leg of the trip? Displacement going home is 24 kilometers because we are, in that case, you're starting here and ending here, 24 kilometers away from where you started. So 24 kilometers divided by 1.5 hours, 16 kilometers per hour. D asks, what is the displacement for the entire trip? You finish where you started, so there's no difference between starting and finish point, so the displacement is 0. And E, average velocity for the entire trip, is the displacement of 0 divided by time, so it becomes 0. For question 15, Voyager 1 spacecraft be 14 billion miles away. How long will it take the radio signals to reach Earth from this distance? Okay, so velocity of the radio signals is displacement over time. Solve for time, we get time is displacement over velocity. But we don't need to call that average velocity. They're traveling at the speed of light. So let's replace average velocity with c, the speed of light. So the time is going to be displacement over speed of light. At this point, it's just a matter of getting proper unit conversions. We want this in MKS units. So we turn right here, displacement of 14 billion miles, 14 times 10 to the 9th. We want that in meters. So 1,609 meters divided by a mile. The miles units will divide out, and we're left with 2.25 times 10 to the 13th meters. So now that we have MKS units, meters and meters per second, time is 2.25 times 10 to the 13th meters divided by the speed of light, 3 times 10 to the 8th meters per second, and we get about 17,100 seconds. And that rounds to about 21 hours. Number 21. A model rocket launches straight upward. Now, don't think... I'm sorry, I'm going to back out of that sentence. Please think. Its altitude as a function of time is given by y equals 82t minus 4.9 t squared. And we are to find the velocity. Well, you take the derivative of y, so velocity is the time derivative of y. And so this becomes 82 minus 9.8 t. Now at this point, when you're doing number 21, it's expected you've only learned up to section 2.2 in the book. But more likely you maybe have come to the end of chapter 2, and by the end of chapter 2, you'll learn that this is the format for the position equation. Y equals v naught t minus 1/2 gt squared. When you get there, you'll learn there's a y naught as the first term, but we just make that go to 0. And when you see this and you relate it to this equation up here, you see, okay, V naught is 82. That's the original velocity. And you'll also learn this kinematic equation, that V equals V naught minus GT. 82 being V naught, G being 9.8. And so here V equals V naught minus GT, and that's what this equation is right here. But the way the book expects you to do this problem is just to take the derivative. Now, 27. World's first supersonic car accelerates from rest to 1,000 kilometers per hour in 16 seconds. What's its acceleration? This is mostly a unit conversion problem. We have V naught of 0 times 16 seconds. We need V with MKS units. So 1,000 kilometers per hour. Let's get rid of kilometers, turn it to meters. So 10 to the third meters divided by kilometers. Kilometers and kilometers divide out. We need to get rid of hours by doing 1 hour over 3,600 seconds. Hours and hours will divide out. And then we have 277.7 repeating meters per second. Now we can say acceleration is change in velocity over time. So V minus V naught, 277.7 minus 0. Divide by 16 seconds, and you should get 17.4 meters per second squared. Number 31. A rocket rises with constant acceleration to an altitude of 85 kilometers, at which point its speed is 2.8 kilometers per second. What's its acceleration? So keep in mind, this is not a projectile that's in free fall. It is accelerating under rocket power, so we can't use, if you're tempted to do so, we can't use that acceleration is 9.8 meters per second squared downward. It is accelerating upward. So here's what we know in this line. Y naught equals 0, V naught equals 0, because it starts on the ground at rest. Y equals 85 kilometers. Let's use MKS units and call that 85 times 10 to the third meters. V equals 2,800 meters per second. So to solve for acceleration, let's use this equation. V squared equals V naught squared plus 2a delta y. Solving it for acceleration, first we let V naught go to 0. Acceleration is V squared over 2 delta y, and you should get 46 meters per second squared. Question B, how long does the ascent take? Well, here's one way you can solve it. Using this equation, V equals V naught plus AT, and letting V naught go to 0. We have V equals AT. Therefore, T equals V over A. 61 seconds. And by the way, the V that you plug in is at the end of the ascent. So 2,800 meters per second divided by the A, 46 meters per second squared. And that'll give 61 seconds. Number 40, the foul ball problem. So it leaves the bat going straight up 23 meters per second. It's in free fall, so A equals negative G. Now notice my which way I'm calling positive and negative. V naught is positive 23 meters per second, so I'm calling up the positive direction. Acceleration is negative G. I'm calling down the negative direction. Question A asks, what's its maximum height? To do this, you need to recognize that at its maximum height, that's where velocity is equal to 0. And we're solving for delta y. So with that information, we can use this equation. V squared equals V naught squared plus 2a delta y. V squared is going to be 0 because we're talking about the maximum height. And we get delta y equals negative V naught squared over 2a. And then we plug in what we know. V naught is 23 meters per second. A make sure you make a negative 9.8 meters per second squared, and you should get 27 meters. That's how high the ball goes. Now, question B asks, how long is it in the air? For how much time? So here's one way to do it. It starts at some height. We'll just call that a height of 0. You can call it anything you want, but we'll just call it 0. Whatever height it starts at, it'll end at that same height. So we'll call that 0. Whatever you called the first one, call the second one, whatever you called y naught, you could call it 100 if you want to. But if you call y the same thing, 100, whatever that number is, it'll subtract away. And you'll be left with 0 equals, and that y naught term goes away, 23t plus 1/2 times a. Remember, a is negative 9.8, so plus 1/2 times negative 9.8. I just wrote minus 4.9 t squared. To solve for t, we can factor t out, and that's leaves us with 0 equals t times 23 minus 4.9t. This gives us two solutions. The first solution is just that t equals 0. That doesn't tell us anything new. That just tells us that at time 0 it was at the ground, and we already knew that. What we want is the second solution. 0 equals 23 minus 4.9t. So you solve it and you get 4.7 seconds. Number 49. Good calculus problem here. An object's position is given by x equals b times t to the fourth at time t. Find an expression for the instantaneous velocity. Okay? So instantaneous velocity, that's just the derivative. So time derivative of b t to the fourth is 4b times t to the third. Now, the second part says show that the average velocity in the time interval from 0 to t is equal to 1/4 of the instantaneous velocity at time t. Well, we already solved for the instantaneous velocity at time t. Now we need to show that average velocity over this interval is 1/4 of this. So, here's how I did it. Average velocity is delta x over delta t. Delta x is change in position, so final position, x at time t minus x at time 0 over delta t. So what is x at time t? Well, we go back up to the original equation. X at time t is bt to the fourth. So there's bt to the fourth. Minus x at time 0, b times 0 to the fourth. That's 0, so this term just goes away. So our numerator is bt to the fourth. And we're dividing by the amount of time that's gone by, which is t. So bt to the fourth over t is bt cubed. Now the problem is asking to show that this, what I'm circling here in the pink, that average velocity is equal to 1/4 of this. And you can see that bt to the third is 1/4 of 4b t cubed. But I set it up here as a proof. So show that average velocity is equal to, and I haven't yet shown it, so I put a little question mark there, equal to 1/4 of instantaneous velocity. So I just plug these values in. bt cubed, is it equal to 1/4 of 4bt cubed? And yes, it is. Number 51. An object's position is given by x equals 1.5 times t cubed. Determine instantaneous velocity and acceleration at the end of 2.5 seconds. Find average velocity and average acceleration during that first 2.5 seconds. All right. Instantaneous velocity, if x is 1.5 t cubed, instantaneous velocity is the time derivative of that. So 3 times 1.5 is 4.5 t squared. And then we plug in 4.5 times 2.5 squared, and you get 28.1 meters per second. Part B, instantaneous acceleration, is the time derivative of velocity. So 2 times 4.5 gives 9t. So 9 times the time of 2.5 seconds gives 22.5 meters per second squared. Question C, average velocity from time 0 to time 2.5. That's the position at 2.5 minus position at 0. And to get those, you plug into that original formula. 1.5 times 2.5 cubed minus 1.5 times 0 cubed. Divide by the time that's elapsed, 2.5 seconds, and you get 9.38 meters per second. Part D, average acceleration, is the difference in the velocities. So velocity at 2.5, which that's actually what we got in Part A, velocity of 2.5, minus velocity at 0. If you plug 0 into this equation right here, you get velocity at 0 is 0. And then divide by the 2.5 seconds that have gone by, and you get 11.3 meters per second squared. And finally, a nice little calculus problem here. 85. Derive this kinematic equation by integrating this kinematic equation. Okay, so these are nice problems when you know what the answer is supposed to get, so you know when you've arrived there. We can start with saying x is the integral of v dt, because that's what the problem says to do. Problem 85 says to integrate that equation. So here's the integral of it. X is the integral of v naught plus at dt. From here, it's just a matter of remembering how to take an integral. So I split it up into two separate integrals. Integral of v naught plus the integral of at with respect to dt. So for the first one, v naught is a constant. I put it to the outside of the integral, and it's integral of it's v naught times the integral of dt. For the second one, a is a constant, and so I put a to the outside, and then it's the integral of t dt. So when we integrate the first one, the integral of dt is t, so this becomes v naught t. Plus, the second one becomes 1/2 t squared, but we're multiplying it by a, so we do 1/2 at squared. Now, each of those integrals had an integration constant. You might call them c1 plus c2, but just let's lump them all together and say plus c. The question advised in the book, it says you'll have to interpret the constant of integration. What is this c? Well, that's going to be the initial position. So this c, I've moved it over here and called that x naught. So here we have the kinematic equation, x equals x naught plus v naught t plus 1/2 at squared.